Hello everyone, I'm Haoran Wang from Institute of Computing Technology, Chinese Academy of Sciences. I'm presenting our work CTA, Hardware-Software Co-Design for Compressed Token Attention Mechanism. Transformer-based models have been widely applied in multiple areas, achieving state-of-the-art performance. Recently, ChatGPT shows that transformer-based large models can significantly expand the boundaries of machine intelligence. Attention mechanism is the key enabler of transformer-based models. It brings to models the ability to model relations between elements with arbitrary distance in sequence. Its formulation features mainly matrix multiplication, which is well parallelizable. It also finds patterns between elements mathematically, which enables using larger amount of no-label data to achieve better performance. However, attention mechanism is no free lunch in that it calculates dense relations between sequence elements. Depending on the sequence length being processed, attention mechanism can count for 30 to 50% of the computation time of transformer-based models. From 2018 to 2022, the proposed transformer-based models have grown over 1,000 times in parameter scale. So, efficient attention mechanism is more and more important. Attention mechanism computation can be divided into 4 steps. Step 1 is to linearly transform tokens to carries, keys, and values, where they are all vectors with same dimensionality. Step 2 is to calculate dot product similarity scores between carries and keys. Here, in S matrix, each row vector lists the similarities of one carry to all the keys. Step 3. Apply row-wise softmax to S matrix, normalizing the similarity scores for each carry. The normalized scores in one row sum to 1, which can be interpreted as attention probabilities that the carry is related to keys. Step 4 is computing the output. Each carry generates one output, which is the weighted sum of values, using the attention probabilities of this carry as weights. To accelerate attention, previous works observed that keys do not contribute equally to the output for a given carry. For those keys having small dot products with the carry, their attention probabilities tend to 0 and can be pruned. But this pruning is specific to carry and changes for different carries, breaking the matrix multiplication formulation for multi-carry processing. This hinders architecture design. Our work aims to accelerate attention with shrinking matrix scale while keeping the matrix multiplication formulation for major steps. Our motivation is that the repeating pattern of tokens is projected into carries, keys, values, which causes repeating pattern in both row and column directions of similarity score and attention probability matrices. This inevitably causes redundant computation. Motivated by this, we propose CTA, Compressed Token Attention Mechanism, an algorithm architecture co-design solution that can substantially reduce complexity of attention, achieving both speed up and energy efficiency. From algorithm perspective, CTA can efficiently compress tokens and reduce complexity of all the steps in attention computation. Now let's look at how it works. We need to efficiently remove semantic repetitions in tokens. We utilize locality-sensitive hashing to achieve this. To give an example, we have 5 tokens x1 to x5 lying in the Euclidean space. We randomly choose direction vectors a1 and a2 from this space, which determine 2 direction axes. We chop direction axes into equivalent intervals. Then we can assign hash values to tokens based on which interval their projection lies on the direction axis. It's shown that if direction axes are sampled from standard normal distribution, hash collision of 2 vectors means short L2 distance between them. Thus, we group tokens with same hash values into a cluster and compress tokens to the cluster centroids, which we compute as the average of tokens in the cluster. Now we introduce the step 0 of CTA, token compression. We propose to utilize two-level compression. In this example, first level compress 6 tokens to 2 tokens. After first level compression, we compute residual tokens as the difference between original tokens and their corresponding first level compressed token, which can be interpreted as the error if we want to approximate original tokens with only first level compression. We then further compress 6 residual tokens to another 2 tokens. Original tokens can be approximated with compressed tokens. For one-level compression, simply approximate token as its first-level compressed token, while for two-level compression, approximate token as the sum of its first and second-level compressed tokens. You can see that with two-level compression, we can approximate original tokens with less information loss. In the following, we visualize vectors as colored rectangles, where two vertically adjacent rectangles connected with dashed line represent sum of two vectors. In CTA, we separately compress query tokens and key-value tokens with one-level and two-level compression respectively. This compression method provides enough accuracy. After compressing query tokens, we get K0 compressed tokens and a table CT0 recording each token is compressed to which one. CT table contains the information about how we can approximate original tokens with compressed tokens. Similarly, after compressing key value tokens, we get K1 and K2 tokens with tables CT1 and CT2. Step 1 is to apply linear transformations on compressed tokens to generate compressed queries, keys, and values. This step utilizes ordinary linear transformation weights, but the number of queries tokens and key value tokens reduce. The computation of these linear transformations decreases linearly as the number of tokens to be transformed decreases. Step 2 is to compute similarity scores. The ordinary similarity computation is quite expensive when sequence length n grows large. On the contrary, CTA computes similarities between compressed queries and keys. An arbitrary ordinary similarity can be approximated as the sum of two CTA similarities. In this step, the numbers of both queries and keys are reduced. Thus, the computation is reduced quadratically. Step 3 is to compute attention probabilities. For ordinary attention, this step normalizes each row of scores by softmax. However, for CTA, we aim to compute attention probabilities that can be used as weights on compressed values. We call this process as probability aggregation. The aggregation result, AP, must be K0 by K1 plus K2 matrix, representing the weights of K0 compressed queries on K1 plus K2 compressed values. The key idea of probability aggregation here is to find a way of weighting compressed values that can approximate ordinary outputs. With this object in mind, we reform ordinary output into weighted sum of compressed values. We take output O1 as an example, split each value into the sum of two compressed values and merge their coefficients. The resulting coefficients circled by red rounded rectangles are the aggregated probabilities. Based on this observation, we derive the following aggregation algorithm. The aggregation process iterates over all items in CT1, CT2. Each time, select two scores according to CT1, CT2, take the exponent of the sum of selected scores and add the result to the same positions in AP. Note that the first K1 positions are indexed by CT1 and the rest K2 positions are indexed by CT2. Here in the first iteration, CT1 and CT2 read 1 and 1. Thus, we select the first score from CT1 part and the first from CT2 part, compute the exponent of their sum, and add to the same positions in AP. In the next iteration, CT1, CT2 read 1 and 2. Thus, we select the first and the second from CT1 and CT2 parts, compute the exponent of their sum, and add to the corresponding positions in AP. After iterating all the items in CT1 and CT2, the algorithm gives aggregated probabilities as desired, which can be used as weights to compute output. Note that in each iteration there is an exponent operation, and there are in total n iterations. Thus, n exponent operations are needed to aggregate one row of scores, which is the same as row-wise softmax in ordinary attention. The total number of exponents is reduced due to less queries. The final step of CTA is output weighting. CTA calculates weighting of compressed values for compressed queries. Both the attention probability and the value matrix are reduced in size. Hence, the computation of step 4 is also reduced quadratically. Now, we introduce the dedicated accelerator architecture of CTA. As can be seen from previous slides, CTA keeps matrix multiplication formulation for major computation-intensive stages. Thus, the CTA accelerator is designed with a systolic array-based computation engine, with processing elements PE and post-processing elements PPE to support multiple computation steps. The other parts of accelerator act as auxiliary modules that does special operations that can't be formalized as matrix multiplication. During step 0, each column of PEs accumulates the inner products between a direction vector and tokens. Each cycle, the partially accumulated inner products are transmitted along vertical data link. Each PPE at the top adds bias to the result and divided by W. Then take floor to generate the hash values. Hash values generated within each cycle belongs to different tokens and lie in different positions of the hash vector, enabling the CRM module to process them on the fly, where tokens are separated into clusters. The CAG module then computes the cluster centroids as compressed tokens. During step 1, each column of PEs accumulates the inner products between a compressed token and all column vectors of linear transformation weight matrix. Thus, each column of PEs generates the query or key or value corresponding to a token. During step 2, each column of PEs accumulates the inner products between a compressed query and all compressed keys. The PPE counts the largest score of first-level compressed keys, then subtract the maximum from the following scores. This helps to control the value range of the sum of two levels of scores, making it convenient to implement exponent operation with lookup table in step 3. In step 3, the PAG executes the attention probability aggregation with hardware parallelism. Each tile iterates the CT1 and CT2 sequentially to aggregate one row of compressed similarity scores. Multiple tiles aggregate multiple rows in parallel. In step 4, each PE forwards its left and bottom input directly to the right and top and accumulates the products in its local result register. During the accumulation, row-wise aggregated probabilities pass through PPE, where they are summed. The sum is twice the softmax denominator. When shifting up the results, each PPE divides the passing result with half of the sum and yields the final output results. We evaluate CTA on several representative transformer-based models and datasets. In this figure, RL and RA bars measure the reduction of computation in linear transformation and the rest parts of attention respectively. For each set of bars, the leftmost RL and RA always equal 1, meaning no compression. We also evaluate the effectiveness of 3 levels of compression with increasing computation reduction. We call them CTA 0, CTA 0.5, and CTA 1. according to their accuracy performance. The green lines above the bars show the model accuracies on the different compression settings. Overall, CTA can achieve good accuracy results with considerable computation reduction. CTA consumes only 44% linear computation and 18% attention computation, while controlling accuracy loss less than 1%. For hardware performance, we compare with NVIDIA V100 GPU and previous state-of-the-art accelerator ELSA. CTA achieves up to 44 times and 28 times speed up over GPU and ELSA plus GPU hardware system. CTA spends 59% latency on attention computation and 34% latency on linear computation. Note that only 7% latency is spent on token compression. CTA also achieves significant energy efficiency over GPU and ELSA plus GPU system. The systolic array computation engine and memory module consume 62 and 29% energy respectively. The lightweight auxiliary modules only consume 9% energy. In the 62% energy consumed by systolic array, only 5% is spent on hash computation, showing that our hashing is relatively lightweight compared to main steps of CTA computation. In conclusion, CTA proposes novel accelerating methodology for attention mechanism in both algorithm and architecture perspective. More details can be found in our paper. Thank you for listening.